mean, that's devotion right there.
That is devotion. It is devotion that is way beyond my
Alex, why is it just not called
my level of commitment. All right. So, what's so?
Physics.
Oh, my.
Physics X. No, I'm not calling it Phys X. Although, that is really witty. I like it. But we're not going to do it. Okay. So, all right, so I'm just going to get started. I was going to say something, but I'm not going to say it because it's really going to trip you up. I'll say it at the end when I turn the camera off. Anyway, okay. Yeah, I'm really nervous. Okay, so today, excuse me, we're going to take what we've been doing. Ariel, pay attention. Oh, you know what I haven't gotten? I haven't got my card though. And seeing Ariel be like a bad boy back there reminded me of that.
Got to raise
So we got Matt Kowalski. Is Jacob here? Jacob's not here.
Eventually, he will. He's like,
Oh wait, no, I've already called these people. I gotta go. Anyway, all right, I'm gonna continue talking while I shuffle cards. Oh, there we go. Gage just got a pretty good one. We'll start with Gage. Anyway, so I'm just gonna start. Okay. So I almost want to read this because I feel like it's pretty good, but I won't read it. Okay, so when a lot of times. We define things that we encounter in physics and math based on something that's pretty concrete, that you can kind of easily visualize or wrap your head around. And sometimes for very practical reasons. But it turns out that in many cases it helps to abstract those definitions, and in abstracting them you can often find a greater range of applicability of the original definition. So to give you a very pedestrian example of this, we know that we've got this whole family of really awesome trigonometric functions. And we can functionally define these and actually evaluate them by constructing a bunch of right triangles with the angle in question as one of the interior angles. Okay, and then what we know is if we take this right triangle and we measure this side, and this side, which we could literally do with a meter stick. Okay, you get a protractor to fix the angle, make sure that's 90, get a meter stick, measure these lengths, and with that very physical, very concrete measurements, you can use the definitions of these things as ratios of sides to evaluate these trigonometric functions. Okay? And so, just as an example, we know that cosine theta is the length of the adjacent side over the hypotenuse, et cetera, et cetera. You can figure out the rest of the ratios if you don't remember. Okay, so that is one way to define trigonometric functions in terms of something very intuitive and concrete. However, this definition is going to be a little bit lacking if I came to you and said, okay, fine, evaluate that. Well, let's follow our prescription. So the first thing that we do is we construct a right triangle with an imaginary interior angle. Nice. Which I don't think any of us can do. But were we to construct said right triangle with an imaginary interior angle, of course here I is the square root of -1, then we could measure the lengths of the sides of that very weird right triangle, compute ratios, and evaluate the trigonometric functions with imaginary arguments. Okay? That's not going to work. So what we would prefer is a definition of these functions that is maybe a more abstract definition, but hopefully would allow us to address what we would get if we stuck in an imaginary argument. And so we might imagine that if I wanted to evaluate, say, the cosine of x, instead of thinking in terms of triangles, we would actually work with its Taylor expansion. So you know how the Taylor expansion works. I'm just going to have 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th plus an infinite number of terms. But the utility of this is that if I give you the number x, or the angle theta, then this is literally just multiplication. I mean, granted, it's an infinite number of these things, but if it's a small value of x, you know, you can truncate this and get a reasonable approximation. But this is something that you all know how to do. It's literally arithmetic. It's multiplication. Okay? So this is yet a different way to evaluate cosine and then similarly sine and tangent. All right? That gives you answers that are in complete agreement with the definition in terms of right triangles.
Yeah.
However, this makes complete and total sense if we introduce an I into the argument. Because we know how to multiply with factors of I. And so if we come through here, really all we're doing is everywhere we see an x, we replace it with ix. And we are just as capable of evaluating that expression as we were evaluating this expression, even though it would be impossible for us to evaluate it using right triangles, because we can't build a right triangle with an imaginary angle. Okay? So what I'm going to talk about today is how we have talked so far about objects and transformations that are very rooted in concrete starting points. But those are not going to be powerful enough for us to eventually describe the things that we really and truthfully need to work with. So what we're going to have to do is take the very concrete starting points that we've gotten familiar with and develop a level of abstraction that gives us the same results, but will later allow us to handle things that we weren't able to handle with the more concrete starting point. Okay? All right, so here we go. So far, we've talked about dynamical objects described by tensors, scalars, vectors, dual vectors, higher rank tensors. We've talked about transformations of those tensors, so rotations, boosts, altogether the set of Lorentz transformations. Okay? But so far, these objects and the transformations of those objects are rooted in coordinate systems. And coordinate systems are very concrete things. You know, we have a space like this room, and we set up a coordinate system in the room. And, you know, the very first thing that we know that we can do with that is we can specify a point in the room by its position vector. Okay? But if you recall, if I consider connecting 2 points by an infinitesimal displacement, then I can build this thing. And if I go to 4 dimensions in space-time, then this becomes the prototypical 4 vector. And then we can talk about how this thing transforms under changes of coordinates, which are rotations, boosts, and there are other changes of coordinates we might consider. But of course, these are the set that leave the metric unchanged and take inertial frames into inertial frames. Okay? So before I said that our kind of basic intuitive starting point was right triangles, and then we abstracted to something more powerful. Here, our starting point is quantities and transformations that are defined with a very intimate connection to coordinates. But we're going to have to get away from this. We're going to have to develop a more abstract way to deal with these things. And what's cool about the level of abstraction is, first of all, it's going to let us talk about something more perplexing than tensors and rotations and boosts as they act on tensors. But it's also going to give us something else that would be useful, and that is a means of comparing groups. In particular, a means of comparing continuous groups. So this is just an extra bonus that we're going to get out of developing this abstract machinery. And so just as a quick reminder, remember if you have a finite discrete group, say even and odd numbers under addition, which Gage is going to help me fill out the multiplication table. What goes here? So even and odd numbers under the operation of addition. If If I add an even and an even number, what do I get?
Okay, even.
Yeah, you get even. What goes here?
Odd,
Yeah, here?
odd, and even, yeah.
Yeah. And if, who's next on my list of victims? Martin. If I instead do plus 1, minus 1, plus 1, minus 1 under multiplication, what goes here? This is easier. 1.
Negative 1. Oh, this is a hard one.
Yeah, negative times negative. Gosh! Hi! No, it's this. Okay? And then we notice, wow, those two charts are pretty much the same thing. In fact, they are exactly the same thing, and we can conclude that those two groups are the same group. Okay? Clearly, this is not going to work for a continuous group. I can't write down the multiplication table for a continuous group. It would take me forever. Okay? And we don't have that much time. It would be nice to have that much time. But there is a certain sense in which, even though continuous groups have an infinite number of elements, we've already encountered the idea that there's still like sort of a subset of important elements that we can kind of put everything in terms of. So for example, when I think about the group SO3, the set of 3 by 3 orthogonal matrices with unit determinant, this describes rotations in 3 dimensions. How many elements are in that group? Wolfgang, how many elements are there in this group?
9.
Ask Caroline how many elements are in the group.
Caroline, how many elements are in the group?
How many different rotations can I do? Ask Franco behind you.
You got my name, didn't you?
Yeah, well, I wanted to call you Wolfgang. I was like, Wolfgang, that's Franco.
Well,
Actually, I was looking at you. I was like, you don't look anything like James Franco. But yeah, I know. But I'm going to call you Franco because that's your name. Okay.
my dad.
How many elements?
Infinite, infinite.
Yeah, there's an infinite number because I can rotate by a continuous parameter. Does that make sense to everyone? So if I say I'm going to rotate by an angle theta, theta can take an infinite number of values because it's a continuous range from 0 to 2 pi, for example. So it's like asking, how many numbers are there between 1 and 0? Well, there's an infinite number of numbers between 1 and 0. Okay? However, there are how many types of transformations that were really distinct in this set? Matthew?
I was just going to say like 1. But there's one matrix you can write that has them all in it. With a continuous parameter, right? Oh no, sorry, 3 dimensions. My bad.
Yeah.
Go around. There's,
Yeah.
Is that 4 then?
3.
Wow, okay.
I think the way we usually say it is we can do a rotation around x, a rotation around y, and a rotation around z. And any rotation can be built by something in x, something in y, something in z. So even though there's an infinite number of transformations, somehow the number 3 is important. Okay? And we're really going to capitalize on that in this abstraction. Okay, so before we actually get into the meat of how we're going to do the abstraction, we might ask ourselves, if I'm going to be comparing continuous groups, what kinds of features is it going to be reasonable to expect to be the same between equivalent groups? So I'll give you a list of a few options. Number of free parameters, abelian versus not abelian, the dimensionality of matrix representations, and just one more, real or complex representations. So are the matrices real valued or are they complex valued? So if I have 2 continuous groups and I claim they're the same, do you think they have to have the same number of free parameters? Yeah, and we'll actually uncover why that's the case in due time. But this is definitely something that we're going to see emerge from comparing continuous groups. What about if a group is abelian versus non-abelian? Yeah, we're going to expect this feature to be the same as well. And again, we'll see reasons of that in due time. What about the dimension of a matrix representation? Do we expect those have to be the same for 2 equivalent groups? No, in fact, we've already discovered that a single group can be given many different dimensional representations. So which one do you pick to compare to another group? Okay, so this is not something we're really going to demand. You know, in your first homework assignment, you were looking at rotations in 3 dimensions in terms of 8-dimensional representations. Okay? What about real versus complex? No, again, in your homework, in that problem from your first homework, you used a real representation of rotations in 3 dimensions, but you also used a complex representation. Actually, you did that for rotations in 2 dimensions. So this is not really something that we expect to have to insist to be the same. Okay? So now we're going to start formalizing all of this. And the good news is that for many of you, you've seen some of this machinery before. Okay? Even though you might or might not be anticipating what we're about to talk about. So we're going to develop the machinery based on our starting point of the stuff we're familiar with. And then we probably won't have time today, but next time we'll extend it to objects that we simply can't handle with the machinery we've developed so far. And then we'll, after that, extend it to the relativistic version. Okay? But here we go. So the good news is that in this class, the groups that we are really interested in are all examples of not just any old group, but things called Lie groups. Okay? And if you want to get technical about it, technically, a Lie group forms a manifold with a differentiable structure. I know you're sitting there reading that, and some of you are like, I know totally what he's talking about. And others might be a little confused. But the idea of a manifold is, loosely speaking, it forms a space. So what I have in mind is these sets of transformations you can imagine as fleshing out a space. And as you move throughout the space, you're moving from one transformation to the next. Okay? And there's technical things that go into the definition of a manifold, and those who took GR would know those technical things. We won't really need them for this course. But the second important part is that it forms a manifold with a differentiable structure. And what that essentially means is that we have a meaningful way to, in a sense, move or take derivatives or look at changes or quantify changes as we move around in this space. Okay? And the thing that makes this technical definition so powerful is that if we consider the space associated with the set of transformations, if we pick a starting point in the space, because it has a nice differentiable structure, we have a way to move around from our starting transformation to other transformations in the space. Okay? Now, let me actually make this more familiar. Okay? So what do I mean by this? Well, you're all familiar with the idea that if I handed you the matrix that is associated with a rotation in the xy plane by 1 degree, so this is just, some 3x3 matrix if you're working in 3 dimensions, and it's a rotation associated with a 1 degree rotation in the xy plane. If you know this single piece of information, you are all capable of immediately constructing the rotation matrix associated with n degrees, where n is any integer. How would you do it?
Matrix cosine, cosine.
Jonathan,
You change 1 to n.
say it again.
1 to n.
Okay, so let us pretend that I gave you this thing and it was some like A, B, C, D, 0, 0, 1, 0, 0.
Oh, you raise it to the n power?
Yes, exactly. If I can rotate by 1 degree, and then I rotate by 1 degree again, and then 1 degree again, and eventually I can get up to anything I want. I don't want you to jump ahead to sines and cosines. Like literally, if you know this, you just do powers of it to get this. Okay? So there's a certain sense in which all you really need to know is this one thing. Now, unfortunately, these are integer steps, so we couldn't do a rotation by 1/2 degree. However, if we were smart enough to figure out what a rotation by epsilon is, where epsilon can be arbitrarily small, then if we know this, we could in principle figure out what the rotation would look like for an arbitrary angle by compounding a bunch of these. Now it's a little weird, right? That, how many epsilons does it take to get a theta? I told you all, the world will never know. I always chew my lollipops. Anyway, so that's kind of a weird, like, how do I compound an infinite number of these to form a finite rotation? And it seems a little bit weird, but the good news is that for Lie groups, there's automatically a built-in mechanism for doing this compounding of infinitesimals. Okay? So again, what I'm saying to you is if I literally gave you this matrix, these would have values. And I said, take this and form that, you'd be like, I don't know what to do. How many of them do I do? Like theta divided by, I don't know how many that is. So I'm going to give you the answer to that question. But at least in principle, if you know how to compound them, then you just do what I just said you do for the discrete case. You put enough of them together and then you get theta. Okay? So, without any further ado, what is that operation? Well, for a Lie group, it turns out that a general element of a Lie group can be written as A, so that's just the generic name of the element, the transformation or whatever. It can be written in the following form: e to the I, g, a, v, a. Okay? So this is what I will sometimes refer to as the exponential map. But we are essentially using a complex exponential to compound these things. All right. So a couple of labels here. The quantity GA generates the transformation associated with A, and VA parameterizes the transformation. Okay, so what do I mean by that? Well, remember how in our discrete rotation example I said if I gave you this, then you could build any rotation by an integer number of degrees, okay? Well, there's a certain sense, it's not precise, I'm just kind of giving you some loose connection. There's a certain sense in which this guy is like the generator. He's the thing out of which you can build everything else, okay? And this guy is the parameter. It's saying, I want to take the generator and apply it this much. In this case, it happens to be an integer. Here, it's just this thing VA. We'll talk about what VA is in a moment. Okay? But this is formal, and there's a rough connection to this, although it's a little bit disconnected, as we'll see in a few minutes. Okay? Now, a couple of things to note. about this expression. If A itself is represented by an n by n matrix, then so is the generator GA. Okay? And we'll see in a few minutes why this is the case. But if this thing is going to be represented by, say, a 3 by 3 matrix, this guy better be a 3 by 3 matrix. Or conversely, if this thing, the generator, is a 3 by 3 matrix, then the element you build up will be a 3 by 3 matrix. Again, we'll see the details of that in just a minute. And secondly, the combination GAVA allows us to combine contributions from different types of transformations. So for example, if I'm talking about rotations in 3 dimensions, then what I would do is something like the following. I would say, okay, there's one generator that gets me rotations in the xy plane, so I could call that GXY. And for that generator, it would get some angle. I might just call it theta. But this is a sum over A. It's a repeated index. So then I would also allow for a rotation in the YZ plane. And it would get its own parameter, maybe call it phi. And then similarly, there would be the possibility of a rotation in the ZX plane, and I could call its rotation parameter psi. Okay? Now this is very important because one thing we know is that if we're doing rotations in 3 dimensions, we don't have to just do a rotation around the x-axis. And we don't have to just do a rotation around the y. We can do a rotation that is a combination of rotations in around the x, the y, and the z axes. And this is the formal way of combining them. So if I want to do a rotation which is essentially built from a theta around in the xy plane, phi in the yz plane, psi in the zx plane, I build this thing and then I cram it in here. And then that will give me the total rotation operator associated with that combination. Spencer.
So is there a composition operator between those two things?
Composition operator between.
As in, yeah.
So if I have a A and a B, can I combine their exponentials?
No, I mean GAVA. Is it GA compose VA as in VA?
You should literally think of GA as a vector of generators, or GA as a vector of generators, or a dual vector of generators. It doesn't matter. Well, a dual vector of generators, and VA as a vector of parameters. And then you're literally just doing sort of component-wise multiplication and adding. I mean, it's kind of like a vector composition, but well, so you're using the word composition. And normally when we refer to composition, we're kind of talking about what is the operation that I use to combine elements of the group. So when I think of composition in this case, I should ask, how do I take an A and combine it with a B? Okay, and there is a sense in which I should be able to work this out from the exponential map in terms of the generators. But this is not. Well, I guess there is a certain sense in which you could consider an arbitrary rotation as a composition of x, y, and z rotations, but it's not. It's not quite as simple. So it's certainly not as simple as just multiplying 3 exponentials together. So what I'm saying is, yeah. So maybe this is what you're alluding to. You might be tempted to say this is e to the I g x y theta e to the I g y z phi e to the I g z x psi. But that is definitely not true, because the g's are matrices, and so this whole thing, you can't factorize it like that. But let me keep going, and you come back and ask me that again at the end.
Okay.
You should have come to Physics X, that's all I'm going to say. Yes, Oreo.
Are you allowed to factor it that way if the matrices commute?
Sure, yeah. But we're not going to expect them to commute in general. Yeah. Okay, so old tips from quantum, if you've seen this before. All right, so what I want to do now is actually work through the guts of this in a very concrete example, which many of you are probably reasonably familiar with. And again, much of what I'm going to talk about today is concrete, and then when we meet next time, we're going to take it and apply it to something which is not concrete at all. So, all right, here we go. So let's consider good old rotations in 3 dimensions, and let's apply this machinery in explicit detail. Okay, so let's just talk about a rotation in the YZ plane. Yeah, I'm going to talk about the YZ plane by an angle theta. All right, that is a transformation. It's associated with rotations in 3 dimensions. So if you will, that would be an element of SO3. Okay, and my argument is that since this is a Lie group, I should be able to represent this in terms of e to the I g yz times theta. I'm only rotating around one axis or in one plane, so my VA is just theta 0, 0. So I'm just going to focus on one of the terms being non-zero. And then we are, of course, immediately posed with a problem. And Madeline? Madeline, this is a matrix, right? I just argued that if this is a matrix, this is a matrix. How do you take the exponential of a matrix? You just put it in your calculator? Like e to the matrix equals? How do you think we might take the exponential of a matrix? In fact, this is kind of a big rule from physics. If you're ever asked to do an operation on something, like at a matrix or an imaginary number, and you really don't know how to start, what kind of really broad tool might we throw at it? Taylor expansion. I don't get it, Matt. What's so funny?
Google.
Oh, Google? That's a Google. Well, you could have Googled it, Madeline, but you know, it's fine. So, Will?
Yeah, so if GYZ is a matrix, then in general is GA like a dual vector with the elements of which are matrices?
Sorry, say it again?
So because GYZ is a component of GA.
Yes.
Okay.
Sorry. So GA, so yeah, I'm sorry, this is a theme in this class. GA is a vector of matrices. But VA is literally, it's a dual vector of matrices. I should have written this as a row. VA is really just a vector of numbers. The parameters are just numbers, they're angles. But the GA is a vector or a dual vector whose components are matrices. We're going to see a lot of that in this class. Okay? Nice. And by the way, you've already seen it, right? Because you know, if I write this thing down, you can think of this as a vector of matrices. Actually, that might not be quite right. I don't want to think too hard about it at the moment, but anyway. Franco.
This is an easy one. So even though RYZ, you know, it's an element of SO3, but it can be expressed as a matrix, you know, n by n or n 3 matrix, right?
Sure.
And you said that ball was also the elements of GA. They
Yeah.
also be n by n matrices. But they're not elements of SO3, are they? Or are they?
Are the G's?
Are the elements of GA also?
No.
Okay.
Okay, so this is important. The GAs themselves are not elements of SO3. That's why I was making this loose analogy to the R 1 degree, R n degrees. The GAs are not themselves elements of SO3. They are what we call the generators of SO3. And we'll see explicitly in a minute that they couldn't be, because I'm going to write them down. Okay? But they are the things from which you build the elements of SO3. Yes?
What are the insides of it? SO3. GA are the components of GA, the matrices inside GA, SO3 matrices.
No, they're
Still
not.
not?
No, and when I write them down, you'll see that explicitly. Okay? All right, so first step, thank you, Madeline. We have to exponentiate a matrix, and we know that what we should do is Taylor expand it. So if I Taylor expand this, just treat GYZ like a thing, and then do a Taylor expansion. Okay, so you don't have to like worry about it being a matrix, just do a Taylor expansion. So if I Taylor expand this, I'm gonna, and I guess I should have called this GRYZ. I don't know why I did that, but I'm gonna stick with what I've got in my notes. Okay, so I have I GRYZ theta, and then I don't know how many of these terms I'm actually gonna write, but I'll write a couple of them. Okay? This is literally just the standard Taylor expansion of e to the x, okay? With which you should all be reasonably comfortable. And now, Madeline, you see why this is useful if G is a matrix, because literally this is just a matrix. This is a matrix squared, which is just a matrix. This is a matrix cubed, which is just a matrix. So this is really just a sum of matrices. It's something we can compute if we were given the matrix G. If I gave you the matrix G and you didn't think about this and I said exponentiate that, you'd be like, I don't know what to do. You just Taylor expand and then it's a matrix arithmetic. Now with that in mind, what is that? That's the identity matrix. Because these all have to be matrices of the same dimension for this to make any sense. And they are, okay? All right, now, here comes the important part. I would really like to know what that G is. Because in principle, if I know what the G is, then I just plug it into this expression, add up the infinite terms when I have some spare time, and the answer is this rotation matrix. That is, of course, not the way we're going to proceed. We're going to start with the thing we know and use it to figure out what the G's are. Okay?
Are the properties of the G's, like such as like hermiticity and stuff, determined by just the structure of the group? So we can always just diagonalize it, solve the matrix exponential that way?
No. Well, I wouldn't think so. But I'd have to think more on that point. But I don't think that that would work in general. So sticking with the particular example that we have in mind, we know what this matrix looks like, right? We're in 3 dimensions. We're doing a rotation in the YZ plane. That's also called a rotation on the x-axis. So this is just going to be a matrix that looks like this. Let me get my minus in the right place. Cosine theta, sine theta, minus sine theta, cosine theta. Okay? Now I would like to realize this as something like this. How in the world do you think I'm going to achieve that? Say it?
Taylor expand
Taylor expand what?
the cosines and sines within it.
Yeah, we can actually just go in and Taylor expand each and every entry of this, okay? So if I do that, you'll discover that I get something like this. I missed that, but I'm going to ignore it. Okay? And there's something here that we could, if we wanted to flesh this out, you know, and make it like look symmetric among all the elements, we could say that this is actually 1 plus 0 plus lots of zeros, 0 plus 0 plus dot dot dot, plus 0, dot, 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 dot. That way, we could literally say there's a matrix plus a matrix plus a matrix where we peel off all the first terms, all the second terms, all the third terms, and then we just write this as a sum of matrices. Okay? Now I'm going to skip a step. Okay? I'm going to assume that we do this, we carefully compare it to this, and from that very careful comparison, we tease out that this thing would have to be equal to 0, 0, 0, 0, 0, minus I, 0, I, 0. Okay? Now I want to make one thing very clear. To take this and compare it to this to figure out this takes a little bit of time and work, but it's certainly not beyond you. Okay? However, if I claim this is the answer, you should all be able to verify that it gives you the right thing. Because what you can do is take this and stick it into this expression, and you should be able to see that if I take this and plug it into this expression, that I generate something that looks like this. Now you might be sitting there asking yourself, wait a minute, Flournoy, these things get arbitrarily high in powers. I see thetas to different powers, but what the hell's going to happen with g and g squared and g cubed? Okay? And that's where we might point out a couple of really nice properties of this thing. If I square it, I get this thing. And if I cube it, I just get back what I started with. There's a certain sense in which the square is acting like the identity in the subspace where this thing is actually interesting. And so if you square it and get the identity, then cubing it just gives you back what you started with. Okay? So with this observation in mind, you can take these g's, plug them into this expression, and actually see that this emerges from it. Okay? So again, this is a lot like, here's an integral, integrated. That can be really tricky. But if I say, this is the answer, can you verify it? You can always verify it by turning around and taking a derivative. Well,
How general is that result with the squares and the cubes and what? Is that true for all rotation matrices or all generators?
well, it's going to have to be useful for all generators because otherwise this is not going to reduce to anything simple.
Okay.
Yeah.
Is it also significant the fact that for G itself, to 1 power, that the bottom right matrix is the polynomial matrix? Bottom right part.
There is a... We'll make a connection to that later. Well, let me. Okay, so so you might be tempted to say, oh, that's a poly matrix, therefore I just put in different poly matrices in that. But well, it doesn't quite work out like that because if I write down what the generator is for, say, a rotation in the ZX plane, if I follow this whole procedure for a rotation in ZX, so now I have, these elements are non-trivial, then what I find is that generator ends up being 0, 0, I, 0, 0, 0, minus I, 0, 0. And then similarly, if I do GR, XY, then, so what I'm getting at, Franco, is where the various components are distributed in these generator matrices depends on which plane you're dealing with. But the spin matrices are always 2 by 2. So you're not moving around in a sense. I mean, you will, if you stare at these long enough, see the poly matrices. And you're just like kind of pulling them apart, sticking them in various places. And we'll make a connection to that later. But it's not like you just drop wholesale poly matrices into chunks of this. Just stuck out. Yeah, well, it's a good observation and one that will definitely play a role with it later on. Okay. Now, let's see. Okay, yeah, all right, good. Yeah. Any questions? Any other questions? Okay, so I want you to realize, like, this is a story which people see. It's very abstract. It doesn't seem to have a lot of utility. At the end of the day, you go through all this fancy machine work to build something that you could have written down in the first place, you know. So I swear to God, the utility of it and the value of it, I will get across to you probably in the next lecture, okay? But I don't want the sort of seeming mathematical sophistication to overwhelm you. I mean, this is all stuff you can work with. It's really just matrix multiplication and Taylor expansions. And, you know, collapsing a Taylor expansion, it's really not that bad. I mean, if you realize this property and go in here, you can automatically see, oh, there's going to be, you know, 1 plus I times theta. Well, anyway, yeah, you'll see it when you look at it in detail. Go ahead.
If you flip, like if you'd written like GR of XZ, does that just flip the sign on the i's? Or does that do anything?
It would, yeah, it would transpose it actually.
Okay.
So now let's come back to the point, the question got asked a couple of times, are the G's elements of SO3? Well, tell me, are these elements of SO3?
No.
Do they satisfy the property that G transpose G equals the identity? Do they have unit determinant?
No.
No. So the G's are definitely not elements of SO3. But using the exponential map, the R's that they create are elements of SO3. The R's do satisfy these conditions, okay? So we've got to be really careful. And again, this is where I probably led you a little bit astray with that example of saying that this kind of generates rotations by an arbitrary. Okay, this is a very loosey-goosey picture that I don't want you to take too seriously, because this is an element of the group, but the generators in the true story are not elements of the group. Of course, we can also see the very big difference, because here, to get an arbitrary thing, we literally just multiply these together, whereas in this case, we have to use this funky exponential map, which is a little bit more sophisticated than just multiplying things together. Yeah, I got hands crossed, American. Just ask questions. Go for it. Yeah.
Is that enough for unitary transformations?
You guys love your unitary. I swear to God, you guys are all about unitary. Go for it.
Well, EVI Hermitian is unitary, and these are also Hermitian measures you made here. So in general, for the groups, or we already can have generators that are Hermitian.
No. We'll see explicit examples of that. Yes.
Robbie, something random. Can you write the G's as a complex Levi-Civita symbol?
Let me actually say what I'm about to say, which is the final observation, and I'm actually going to write the Levi-Civita. So you'll get your Levi-Civita. I'm not going to do exactly what you're suggesting, but I'm going to make a connection to that in just a second. Okay, so okay, so the one question that you might ask is, I've done this, and I've gotten these 3 matrices. So I want you to note there are 3 of these things, because there are 3 generators of SO3. But you might ask yourself, are these unique? Are these the only set of 3 generators that you could use? And the answer to that is no. There are actually many sets of 3 matrices that will do all of this for you. But then again, we also know that this representation of rotations is not unique. Because after all, to write this, I've chosen an x, y, and a z axis. And then I've chosen rotations in this plane, and this plane. But I could have just as well chosen a different set of coordinate axes and defined my rotations in those planes. And those rotation operators are non-trivially related to these. And similarly, the generators for those rotations would be non-trivially related to these, but each of them would form a completely consistent story. Okay? So the answer is that if you want to get from one set of generators to another set, you're really just thinking about the impact of a coordinate transformation, but how it changes the generators. Okay? Now, everything, and by the way, if you want to go back and think about this in the deep way of there's a manifold of the transformations. So you might say, well, in this picture of the transformations is forming a space, what are the generators? Well, what the generators are is they are essentially a basis in the tangent space of the manifold around the identity. And with the basis in the tangent space, that then allows you to propagate throughout the space with the differentiable structure. So just, again, making a connection to the sort of hoity-toity, mathy, spacey version of this. But we're not really going to work with that too much. All right, so everything that I've done so far is clearly extremely coordinate dependent, right? I started with 3 by 3 matrices. That implies that I'm talking about x, y, and z. Okay? But I would really like to get away from coordinates. Remember, coordinates are very concrete. They're very like, you know, they're things we can visualize and work with and measure. But as long as I'm hanging on coordinates, I'm not going to have the proper level of generalization to be able to talk about things that are weirder than coordinates. So I would like to take this story and write it in a way that doesn't rely on coordinates. Okay? So one thing we can do is we can say, well, can I get to these g's without going through this route? Okay? Or is there a way that I can say or define SO3, or rotations in 3 dimensions is what I should say. Is there a way I can define rotations in 3 dimensions without ever referencing these matrices? And the answer to that is yes. What we can do is, and you can do this for Lie groups, is you can specify. So instead of defining coordinates and then talking about how the coordinates change under rotations, we can instead specify the Lie algebra of the group. So what is a Lie algebra? Well, many of you have taken quantum and know what a Lie algebra is. A Lie algebra is based on a commutator where I'm basically writing down the algebra of the generators. So what I have in mind is if I take a generator, GRYZ for example, and I form its commutator with GRZX, okay, do we all know what the definition of a commutator is? Okay, I do the first one, then the second one, and then I subtract what I get from reversing the order. That's just a definition. I haven't specified anything yet. Okay? But if I tell you that this has to be equal to IGRXY, then I'm telling you something interesting. Okay? Now this is one concrete statement of the Lie algebra. To say it more generally, we would write something like this. If I take the generator, the ith generator, and form the commutator with the jth generator, then the general expression of this is I times the Levi-Civita on GK, where you're hopefully all rudimentarily familiar with the Levi-Civita. If you do cyclic permutations of the indices, you just get +1. If you interchange any 2 of the indices, or equivalently an anticyclic permutation, you get -1. And if you repeat any of the 2 indices, you get 0. Okay, so you can really just think of this thing, it's a crazy 3-index object, but it's just a collection of numbers. 1s, -1s, and 0s, depending on the order of the order and the identity of the superscripts.
Should the I and J indices be down on the Levi-Civita symbol?
Yeah, actually, yeah. Well,
this doesn't really matter.
It doesn't really matter. Yeah, we use. I get a little anxious. So in the space of the generators, you have a trivial metric.
Right.
But, so it doesn't really matter whether you write them up or down, but, so what Brooks is saying is, if I really wanted this to work out index-wise, I might write something like this, in which case you'd ask, well, what the hell is this? What's a generator with an upper index? So then instead, as he suggested, we might write it like this, but then writing down the rules for this look a little wonky. But the up and the lower indices don't really matter in this context, okay? So you can write it like that if it makes you feel better, and then you still just follow the same assignments of +1, -1, and 0 of indices, or cyclic, anti-cyclic, or repeated. Okay? Notice, so for example, if I repeat 2 of the indices, so if I say commutator of GI, GI, well, what's that?
0.
That's 0, because it doesn't matter what order, which is exactly reflected by that statement there. Okay? Now, here's the important thing. We started with a very coordinate-dependent definition. We said, I know what rotation matrices look like. I have this machinery, the exponential map, in terms of the generators. And by comparing it to this very coordinate-dependent starting point, I unearthed what the generators looked like. I can take the 3 generators I found, compute all of their commutators, and I will discover this general rule. Okay? That is one direction in which you could flow this argument. But a completely backwards direction is to say, I'm going to start here. And I am going to find a set of 3 by 3 matrices which satisfy this. Okay? The 3 by 3 matrices which satisfy this, at least one set of them, would be exactly the 3 matrices I wrote down. And then using those 3 matrices and this map, you could work backwards to this. All right? So you could start here and end up here. Of course, you could start here and end up here. But what's important is we're going to be able to start here and end up at things that have nothing to do with coordinates, like ordinary rotations do. Okay? All right, so we'll talk about that next time.
The algebra